Hello class, Professor Anderson here. Let's talk a little bit about electric potential and electric field and how those two things relate to each other. So let's go back to a very simple picture. Let's say that we have a positive charge and we know that the electric field lines point out from a positive charge. So our electric field lines look like this and they are radially out everywhere. And you can draw as many as you like, but let's just draw this many for now. Okay, so there's my electric field. Now, we know what the electric field of a point charge looks like. It looks like this. E is equal to 1 over 4 pi epsilon naught Q over r squared, and then it's in some r hat direction. Okay, that's radially outward. So if it's a positive charge, they're radially outward. If it's a negative charge, they're radially inward. Okay, but what about potential? Potential, we know, is given by V, and potential for a point charge, that pen's not working. Hold on, let me see if I can fix it up. Potential for a point charge V, let's try this one. There we go. Potential for a point charge V is given by the following. 1 over 4 pi epsilon naught Q over R. Okay, remember, this is a scalar, okay? Whereas the electric field is, of course, a vector. And that's why we have the r hat over there, and we don't have any vector sign on this side. All right, how do those two things relate? Well, they look very similar. I mean, they both have Q, of course. They both have this 1 over 4 pi epsilon naught. But this thing has a 1 over r, where that had a 1 over r squared. How do I draw the potential in terms of this function right here? Well, one way to think about it is the following. If I go out a distance r from the point charge, the value of the potential right there is V. And since it doesn't depend on direction at all, it only depends on distance, anywhere I am r away from that point charge, I will have the exact same potential. And so this is something called an equipotential surface. Anywhere you go on that surface, you get the same potential. Okay? You don't just have to draw one of these, you could draw quite a few of them. And each one of these surfaces will have a unique value, but it is an equipotential. All right, so let's see if we can say a few things about that picture. First off, the equipotential surface for a point charge is a sphere, right? We've drawn it in 2 dimensions, but you know that this really occupies a 3-dimensional space, so it is a sphere. The second thing that you notice is that it always makes a right angle with the field line. So everywhere here, it makes a right angle, okay? These things are perpendicular to the E field. If you move along this equipotential surface, you are not changing the magnitude of the E field that you see, and therefore it doesn't require any work to move along that equipotential surface. Okay, let's see if we can make a little bit more sense of this, how these two things relate. How do I get from E to V, or better yet, how do I get from V back to E? Either of these describe this idea of the electromagnetic field, in this case just the electric field. One you can get from the other you can get from the one. So the question is, how do we relate E to V? It looks like if I took V and I divided by r, that would be equal to E. But that looks a little strange, just dividing by r. What if instead we did a derivative? Does that work out? Let's try it. All right. V is this. So dv dr is the derivative of q over 4 pi epsilon naught r. All right. I can move some stuff outside of the derivative because it's a constant. Q over 4 pi epsilon naught. That's no problem. And then I just have the derivative of 1 over r. But what is the derivative of 1 over r? It's the same as the derivative of r to the minus 1. Sometimes this is easier to think about. And the derivative of r to the minus 1 is, of course, minus 1 times r to the minus 2. And so look what this becomes. We get negative q over 4 pi epsilon naught 1 over r squared, which is close to what we have right here, but not exactly, right? The negative sign is not there. We also have an r hat hanging out here that we don't have there. And so this is where we employ a mathematical tool called the gradient, and we write the following. E is equal to the negative, I'm going to pick up that negative sign, del of v. Okay, E equals negative del v. This thing right here is the gradient. Okay, and that is a gradient. And the gradient is a derivative with a direction. So, for instance, if we're only worried about the r direction, like we are with a point charge, the gradient is just d dr with an r hat. Okay? Or if you don't like it if you don't like writing it like that, you can write it like that. Okay? If you have other coordinates, then you can write the other terms as well. But let's not worry about the other terms just yet, except for maybe Cartesian. How do we write this in Cartesian? In Cartesian, the del becomes x hat del del x plus y hat del del y plus z hat del del z. Okay, whoops. That should be a del z. And that now will tell us what direction the electric field is, right? Whoops, I forgot my arrow on top of the electric field. The electric field is in this particular direction, x hat, y hat, or z hat, or in the case of rotational symmetry, spherical symmetry, r hat. Let's try a very simple example of this. Let's try a simple example of calculating the electric field if we are given the potential. And let's say that the potential is the following. It's an XYZ coordinate space, but we're just going to let the potential equal some constant, and let's say that that constant is sigma over 2 epsilon naught z. Okay? Constant and then multiplying by z. So if we think about the coordinate space here, let's draw it out. We've got an XYZ coordinate space. Here's our x, here's our y, here's our z. And what we're saying is the potential grows linearly up in z. Okay, so we have an equipotential surface that is going to look like this. And this is a particular value of V, and it is up here at a height, Z. Okay. How do I now calculate the electric field in this region if all I'm given is the potential? All right, I think we can do that. We go back to this idea that the electric field is negative del V. Again, don't be scared of that thing. It's just a derivative with a particular direction. Okay. In this case, we only have the Z component in our potential, and so the electric field is going to have to only depend on Z. It should be pointing in the Z direction. But let's be explicit. What is this gradient? The gradient is x hat del del x plus y hat del del y plus z hat del del z. Okay, these are just derivatives. These are in fact partial derivatives, but don't be too scared of those partial derivatives. Now all we have to do is take this and operate on the potential V. So let's see what that looks like. Del V is going to be x hat del del x of V plus y hat del del y of V plus z hat del del z of V. And V is this thing right here. Okay, so let's see what happens. Del del x, the derivative with respect to x of sigma over 2 epsilon naught times z. There is no x in there, right? This thing, in fact, goes away. That becomes 0. What about the second term? Well, you can probably see right off the bat that this thing is also going to go away because there's no y in there. There's only a z. So this thing goes away. Boop. And now the last term we're going to hang on to because there is a z in there. Z hat del del z of sigma over 2 epsilon naught z. All right, but we know how to do that. The z hat's just hanging out in front. We have sigma over 2 epsilon naught, and then we have the derivative of z. But the derivative of z with respect to z is just 1. And so this whole thing becomes sigma over 2 epsilon naught z hat. Okay? That is what the electric field is if the potential has this behavior. What could possibly make an electric field like that? What sort of charge distribution would make this electric field? Well, let's be specific, right? When we write E, we have to include the whole thing, which is not just the del, it's the negative. And so we get negative del V, which is negative sigma over 2 epsilon naught in the z hat direction. All right, so this is saying that the electric field is pointing down here, and it is constant everywhere. Okay? It is not increasing or decreasing in magnitude. It is just everywhere negative with this value out in front, sigma over 2 epsilon naught. What could possibly make an electric field like that? Well, turns out what can make an electric field like that is a sheet of charge. If on this sheet that I just drew, I put plus charges everywhere, then this is exactly the E field due to a charged plane. Take a plane, put charge all over it. What do you get for your E field? You get sigma over 2 epsilon naught. The direction, of course, is determined by whether you're above the plane or below the plane. Okay? All right, so that was one example of how these two things relate. Let's try some more. Hello, class. Let's take a look again at an example of calculating the E field from a certain potential. And so let's say that we have a potential V, which looks like this. Sigma over epsilon naught with a negative sign out in front, and then we'll put a Z on there. Can we figure out what the potential is from this? Okay, what is E? All right, let's think about the coordinate space here. We'll go back to our good old XYZ coordinate space. X, Y, and Z. And now let's see if we can identify what this potential is going to look like. It says the potential is 0 right at the plane, and then it gets stronger in the negative going up, and it gets stronger in the positive going down. So if I think about a couple different regions, let's say up here, this has a negative value, right? Because Z would be positive, the negative sign out in front would make it a negative potential. But what about down here below the plane? Okay, and these sort of planes that I'm drawing are, of course, equipotential surfaces. Since Z is negative down here, this would be positive potential. All right. How do we calculate the E field in between these two? What do we do? Well, we know that E is negative the derivative del of V. We only have Z to worry about here. So we don't have to worry about X derivatives or Y derivatives. This whole thing simplifies to negative Z hat del Z of V. We know exactly what V is. It is sigma, negative sigma over epsilon naught times Z. And now we can pull some stuff out. The negative sigma over epsilon naught comes all the way out in front. The negative signs cancel, and we just get sigma over epsilon naught. And then we just have del Z of Z, and we still have our Z hat hanging out. All right, del Z of Z is just 1, and so this whole thing simplifies to sigma over epsilon naught Z hat. This is what the E field is given that potential. What does that look like? Well, it says that it is everywhere pointing up, and it has a constant value of sigma over epsilon naught. So in this region between the plates, we've got an E field that is everywhere pointing up. What could possibly make an E field that is constant, that points everywhere up? We know this. It is the good old parallel plate capacitor. I put a bunch of positive charge down here on this plate. I put a bunch of negative charge up here on the top plate. The electric field points away from the bottom plate towards the top plate and is uniform everywhere as long as those plates are big compared to their separation. Okay, this is still the approximation that it is infinitely large plates. And what you'll remember is that the value in there is sigma over epsilon naught. Remember, when we just had one plate, it was sigma over 2 epsilon sigma over 2 epsilon naught. So it was half of this. But by adding the second plate, you essentially double the electric field in between the two. Okay, so that's what the electric field looks like. And now it makes sense that positive charge down here leads to positive potential, and negative charge leads to negative potential. Okay, so there is a potential difference here, delta V, which is just given by the difference between those two potentials. All right, hopefully that makes sense. Cheers.